Hello, math fans, friends, and family. I'm a longtime professor at the University of Washington that has started to make random, unusual math videos on interesting problems I've encountered over the years. This also gives me a chance to share a little bit of what I do and a little bit of what mathematics is about with my family. Again, I'm not claiming that anything I will discuss is earth-shattering, just interesting, and I'll use it to talk about what I like. This particular video is brought on by geography. I have many people in my family and friends that are big fans of geography. In particular, I have this friend Rob. We talk wonderful man of the community, coached my kids in soccer, and has been a wonderful part of our lives. He loves geography like me. We constantly are searching for unusual small islands from the world to research. Yes, I'm weird on many levels. Okay, so anyways, I wanted to say I thought of this problem. I've been making a collection of problems to discuss. And I was thinking about this problem about that the temperature on two sides of the earth are equal. I remember encountering that somewhere in my studies. But that just got me thinking about geography. So I'm really going to talk about geography here and then mix in a discussion about the intermediate value theorem towards the end. So there's this statement in math that says, at any moment in time, there are two places on opposite sides of the earth that have the same temperature. It's actually not hard to prove that. What's hard is to say exactly where it is. But I'll leave that for the end. What got me kind of investigating this idea of two spots on Earth that are diametrically opposed. And there's all sorts of maps. I did some searching, and I'll show you some visuals in a second. I looked for, the antipode for New York. It gave this as the closest city. The truth is, it's like in the Indian Ocean. But I just thought it was interesting the sizes. I looked up Seattle. That's approximately that's where the University of Washington is. And it's in the middle of the Indian Ocean. The closest city is this, I don't even know how to say it, Port au François, on the Desolation Islands. The Desolation Islands are what you might think the name is suggesting. One of the most remote places on the planet is what it's known for. It's this little island way far away, more of a staging point. I think it said that at one point there was a elephant seal blubber factory or something that, but really it said that only a few people live there, and they're typically planning to explore Antarctica. They said one of the best matches between two bits of land is this little spot in Spain, Coruña, and Christchurch, New Zealand. That those are almost a perfect match, one of the best matches in the world. And there aren't very many good matches, so that was sort of interesting. I found this map. Most of this is just things I found online. This is Wikipedia. They give both versions, but you can see how much of the land hits water. Only these certain spots, I guess that would be Argentina and China, overlap a little bit. Canada, Antarctica. So there just isn't that much. Maybe some bits of Indonesia that hit there, and then it's scattered. What I read was it's estimated that about 15% of Earth's land actually has an antipode that's on land. I don't even know if I'm saying antipode correctly. Anyways, and then I found this map on Wikipedia that said, okay, there's these spots that overlap. So just a quirky little thing. I gotta look up medicine hat. That sounds interesting. But my comment here is about this thing I thought of. So we're going to talk briefly about this so-called intermediate value theorem, which says this. So basically, if you have a function, and you have some starting place, and you have an ending place, and you connect them in a continuous way. So you have a function, it's a continuous way. I'm not going to get too precise. It has to hit every value in between. That can be used to prove things must exist, even if you can't exhibit them. And that's an important thing in math when we know something is there. It's worthwhile to search for. So anyways, the first proof I saw that encountered this was the story of a monk. So here's this hill. Here's this monk down here. A monk looks a lot like a stick figure. And at 8 a.m. one morning, he climbs up this hill, takes his time, maybe stops somewhere in the middle and has lunch, gets to the top, and there's this temple up there. He stays there overnight, and maybe he gets there. It's a long hike. He gets there at 8 p.m., he stays there, meditates, and then the next morning he gets up at 8 a.m., so here he is again. Now he's green. I don't know why. 8 a.m. And he walks down the hill. 8 p.m. This is the kind of classic example of the intermediate value theorem. And he's in a hurry. He goes much faster the second day. Can you prove that you're guaranteed to have a place where he was at the same place at the same time both days? And it has to be. It's continuity. If he's at each space along the way, he will have to cross paths. You can think of that in many different ways. You could talk about his distance from the ground if you want, distance from down here. So initially, the first day, 8 a.m., let's say this is 8 a.m., and this is 8 p.m. This isn't interesting to you, that's fine. But he walks, he gets to the top of the mountain. The second day at 8 a.m., this is his distance, whatever this is, where he's at the top. And then he walks, and it doesn't matter. There's just no way to avoid. He could even go really slow, but he will have to cross. I don't know where it is, but because of continuity, he has to cross. So there is a place somewhere along there that he was at the same place at the same time. I know that had to happen. So there are various things where that can maybe be helpful. This is more mathy, but it does help us prove some things. So specifically, I'm going to show you a little picture. I made a couple visuals here. Oh, first I found lots of websites that had these maps. So thank you to everyone who has made those to make it so you can play around with them. Just search for Antipode Maps and you can find a lot. I teach 3D calculus regularly. We talk about intersections. So if you're one of my students, we'll find the intersection of these and we'll talk about how you can parameterize them and animate them. And I've made lots of things like this. So imagine this is the Earth and we have what we sometimes call a great circle going around it. There's lots of great circles. I have a couple here to see. So I've put 2 points that are diametrically opposed to each other. And I'm going to let them go. Here we go. I do lots of this in my classes. Especially during the pandemic, I made lots of visuals. Here it goes. Okay. So the proof, at some point along this great circle, these two things, if you were to take the temperature at those two spots on Earth, at some point they're going to be the same. So why would that be? So the typical proof goes like this. Let's pick some starting point, and maybe this will be our temperature. And let's take the temperature on the other side, and let's do our temperature minus the temperature on the other side. And that's either going to be a positive or a negative number, or 0. And if it's 0, we've already found it. So assume it's a positive number. Let's say our temperature is bigger than the other side. And then let's give a function that represents the difference in temperature as we go around. Okay, temperature changes in a continuous way. So, if the temperature here is, 32, maybe and it eventually gets to 40, it had to go through the numbers in between. That's the continuity assumption in this proof. So anyways, as we move, that function is going to be changing, the difference in the temperature. So let's assume it started positive, and then it was still positive, with more temperature on our side, positive, and then at some point you'll flip and you'll be on the opposite side. Now the difference has to be negative. So we're saying assume all of this, we're shifting around at a given moment. We're freezing time, and you have taking all the temperatures at that moment. So now if you do our temperature, we're now on the far side. We're over here. If you do our temperature now minus this temperature, it's now going to be negative. So if the original thing was we were 30 degrees hotter, on the other side, go around, we're going to be 30 degrees cooler. So the difference is negative 30 there. The difference on this side is positive 30. And now you can see where I'm going. It's just like the monk problem. If we went from a positive 30 to a negative 30, and you have to hit every value in between, somewhere along the way, it had to be 0. The difference had to be 0. I have no idea where, but somewhere along the way, the difference was 0. And there's probably a lot more. So the surprising part about this proof is it doesn't really prove that. It proves that no matter which circle you pick around the Earth, there's going to be 2 places on opposite sides that have the same temperature. People find that interesting. I don't know if I find it interesting or not. I just wanted a chance to talk about geography. Here's another one. Ooh. Going around. I was going to make this dot bigger so they match. So those people that take Calculus 3 from me, you'll get to see lots of visuals like this. All right. So that's really all I wanted to say about that. I was trying to search online for other examples of this. I did see some posting about if you have some room and there's a ceiling fan, I don't know, like this ceiling fan blowing air around. Sorry for the ceiling fan blows air, it blows some air this way, it blows air some air this way, it swirls around the room. So supposedly you can use continuity. I haven't really thought about this, I just read it, to prove that somewhere in the room the airspeed is 0. And I suspect the argument goes like this, if I think about it a little bit. So at a given point, maybe we'll say if the wind is going that way, we'll say the velocity is positive. I've never really thought about this. This is just a sort of thinking. And let's assume if the velocity is this way, that it's going to be negative. Okay, so we know there are places where the velocity is positive and the velocity is negative around that fan. So there's places in the room where the velocity is positive, there's places in the room where the velocity is negative. So let's take these 2 spots. Maybe here's a spot, just randomly picking one point where the velocity is positive, meaning going that way, and one point where the velocity is negative. And then if you connect them and walk along that line, at some point, if the velocity changes in this continuous way, at some point it will have to be 0. So that's how these proofs go. I think that particular one I didn't do very well. We'd have to think about a little more. I tried to look up, because my friend is into soccer, examples of the intermediate value theorem for soccer. But I didn't. The example they said was, if you need your team to be at a certain level during the game of energy, and maybe it's too low at one point and higher, you had to pass through all the. But I was like, that doesn't really sound that mathematical. Anyways, thank you for listening. I found this sort of interesting. This idea of using continuity or the intermediate value to prove something exists actually is really fundamental, and a lot of kind of foundational things when we talk about mathematics to say, because often it's hard to prove that something's happening. So if we can just prove it's happening, then it's worth searching for. So in math, we talk about, is there existence? And that's sometimes something we have to use an unusual technique like this to prove. Is it unique? Is there just one answer? All all those things are important because we don't want to be solving if there is no solution. Okay, hope that gives you a little different perspective. I plan to make lots of different videos. This was kind of an unusual one, but thank you for listening.